we're going to look at how can we use the code we pushed online on GitHub in order to reproduce the result we've presented in our paper, Tractable Approximate Gaussian Inference for Bayesian Neural Network. So go on GitHub, you can download the code we've put online. Then you can open MATLAB. The first step to do is going to be to go in MATLAB and go in your environment, set path. You're going to add with subfolder the file you would have downloaded from GitHub. So in that case, in my case, it's here. So code, perfect. You take your code, add with subfolder, everything is in here. All the function for the codes are in the function directory, and all the other contains all the data set that we've tested for. So you can open, okay, save and close. Then you just set your current path to the folder you want to evaluate the code for. So the first one we're going to look at is going to be the toy example. So if you look at toy example 1d.m, this is in the toy example folder. We're going to see this is how we can reproduce the code. So the first part here is simply to define the synthetic data. Then we're going to say, do we want to use GPU or not? What kind of data type we want to use? So half, single, or double. So now I recommend you to use single. Number of input covariates, output. So in this case, it's going to be automatically calculated. What is the batch size you want to use? 1. This is going to be the configuration of your network, okay? The number of input layer, of hidden units on your input layer, the number of hidden units on your first hidden layer, number of outputs, okay? If you want to have, instead of having a single hidden layer, I want to have 2 hidden layers. If I want to have 3 hidden layers, if I want to have 4 hidden layers, okay? This works as simply as this. Then here, how many epochs do you want to train for? So number of epochs max. This is going to be your factor for initializing the bias and the weight parameters. These are going to be coefficients that multiply the initial weights on all the layers. You can have different activation functions. So you can choose from ReLU, soft plus, CDF, sigma, tanh, etc. And then everything else is just simply executing the code. So in that case, if we execute directly that function, so you can see that here it do the calculation and it plots at the same time what's going to be the result as a function of the number of epochs. So you see that initially it started with a really crude training, and then as we increase the number of epoch, the performance increase as well. So in black, you see the log likelihood on the training set, the points are used to train the model. You see in pink the performance on the validation set, the point that were not used to train the model. So what you can see here is that we have an optimal here just after 20 epoch, beyond which the performance decreases. Okay, so this is what you would obtain here if you run the toy example 1D. So be sure to be in the current folder being in the same as here. So if instead of using the toy example, we can use, for instance, the Boston housing setup. So Boston housing. So you can here, if you want to run this, you're going to run the Boston housing regression problem, where again, you have here the configuration of your network. You're going to have your parameters, for instance, sigma v, that you can define here. And depending on what you're going to use here, do you want yes or no to optimize for sigma v, the variance parameter of your observation layers? So do you want to optimize the number of epoch or RAM for a fixed number of epochs? What's going to be the number of epochs you want to search for? If you want to do the cross-validation that was used in the benchmark, how many folds do you want to use? What's going to be the ratio between train and test set? The number of split, okay? All of this is possible with the code. And you also have the same thing for this time, the MNIST, the classification problem. So if instead of Boston housing, we'll look at MNIST, so you're going to see the same thing. How is it possible to do the classification, but this time using MNIST and still the same architecture?